Hello, this is Jack Jackson. This is the start of our fourth playlist for this course in college geometry. Each playlist corresponds to a chapter in my notes or textbook, and it also corresponds to roughly 1 week in my college geometry class. So, in our study of unified geometry so far, we've done several things. In the first week, we established some introduction to the course, a little historical background about geometry, and some of the foundations of a axiomatic system. In the second week or second playlist, we looked at some basic incidence relations and postulates there, and we established some relationships among points, lines, and planes. Okay, and then we followed that up in our third playlist by looking at the concept of between and distance. And along the way, we talked about um, defining a line segment and array. And we talked about formally what we mean by distance metric between and a coordinate system for a line. We also postulated the existence of a distance metric and a coordinate system for any line, and that allowed us to use measuring distances and to define line segments and arrays. We use this ruler postulate to prove propositions about distance and order. In this manner, we were able to prove his proposition statements about order and meaning of between, which David Hilbert took as postulates. And as you know, we have um, a different theme basically each week. And so our focus this week will be on angles. Now, last week we also introduced 4 infinite geometries that we're going to be doing in parallel that are all part of unified geometry. Of course, the classic Euclidean geometry, but then also taxicab geometry, hyperbolic geometry, and spherical geometry. And we introduce GeoGebra tools for examining all of those. So this week our focus is going to be on angles. And we're going to proceed in a manner similar to our study of line segments last week. We'll first define an angle, and then we'll informally investigate how to measure angles. Formally, we will postulate the existence of an angle measure metric, and we'll then use it to prove some basic propositions about angles. So in that way, it's pretty similar to the way we looked at line segments last week and distance last week. Okay, so here's the first thing I want you to do, if you can. Okay, see if you can define an angle. Now, I'm assuming at this point that you maybe know what an angle is from previous study. Now, there's a couple of different things we may be looking at for angles, but the definition I'm looking for will define an angle as a geometric figure, that is a set of points from our geometry. And it should be done in such a way that it will apply to all these different geometries that we talked about. So I'm going to ask you to actually pause the video and think about that just a minute. See if you can write down what you think a definition of an angle would be, and then we'll go over what it actually is here and see if you got it right. Okay, press pause now. Well, an angle is going to be the union of two, but not necessarily distinct rays with a common endpoint. Each of the two rays is called a side of the angle, and the common endpoint is called the vertex of the angle. So again, this makes the angle a geometric figure that is a set of points, not a number. And we will name an angle by 3 points. The middle point is the vertex, and the two other points are non-vertex points on the two sides, on the two rays. For example, angle ABC, which we'll use this notation right here, is the union of ray BA and BC, so that B is the vertex. It's the endpoint of both of these rays, and that's the common endpoint will be the vertex B. The rays BA and BC then are the sides of the angle. Now, so we're going to name angles with 3 points. One on one side, then the vertex, and a point on the other side. Okay, if there's no confusion, we may also refer to an angle by its vertex only, such as, say, angle B, like that. Now, the only kind of way we can get by with that is if there's only one angle that we're under consideration that has B as its vertex. And let's use this symbol here for angles. As far as working with Word, you can get it from the Insert Equation Symbols palette in Word. Let's see if I can actually pull that up. So I have mine set up to where it's here. Let me see where, right here, this one right here. Here, and we can go down to Geometry, and there's the symbol right there. So you just click on that, and you'll insert the symbol. Okay, or of course you could just copy and paste this here if you have my actual document here. As with any of our definitions, we will use this definition in unified geometry, so it's exactly the same definition whether we're talking about Euclidean, taxicab, spherical, or hyperbolic geometry. And we can use the same definition actually in any geometry as long as we have previously defined what is meant by a ray. Of course, the way an angle looks is different in each of these geometries, perhaps, since rays may appear different in these geometries, something we looked at last week. You will be constructing and measuring angles in the homework task for this week if you're in my class. So in general, please carefully memorize all definitions. Stating definitions from memory is always a good source for quiz or test questions. Now there are two special degenerate forms of angles, straight angles and zero angles. So let's define these things. A straight angle is the union of two opposite rays. In other words, a straight angle is actually a line. A zero angle is an angle formed by the same ray twice. In other words, a zero angle is really just a ray. A proper angle is an angle which is neither a straight angle nor a zero angle. Now, some textbooks do not count straight and or zero angles as angles. In those treatments, what they refer to as angles, we will call proper angles in this course. So, there's an illustration of a Euclidean angle. This one's constructed in Geometry Sketchpad. When you copy from Sketchpad and make a video, a static picture of it, it will place the little arrows on the end. This indicates that this goes on forever. We have the union of two rays with a common endpoint. Okay, so the rays go on forever, so the two sides of the angle go on forever, but of course the page doesn't go on forever. So we'll just put a little arrow at the end there to indicate that it goes on forever. Okay, when you use GeoGebra and do a copy of an angle, which I can show you some in a minute. Actually, you can go ahead and go down. Here's a couple of angles copied from GeoGebra. Notice that it does not put the arrows on there. I'm not going to require us to go back and force an arrow on there or anything. That's not something we actually need. But you should realize that they do go on forever. Be sure to notice the differences among these three things right here. AB with this is a line segment. This one here is a ray with the endpoint A. This is the full line going through A and B. And contrast that with just AB, which is a distance, it's a number. So, in other words, don't just construct a line segment, say in a homework task, when you need a ray or a line, and don't construct two line segments, say when you need an angle. So this in GeoGebra is not an angle. It's the union of two line segments with a common endpoint, not the union of two rays with a common endpoint. So this is not an angle because it's not two rays. So when you're constructing, if I say construct an actual angle in say GeoGebra, that's the angle you want to do. It's not the measure of this object. It's not any kind of marker that we might put on it. It's just two rays like this up here. Here's what it looks like. Here are a couple of different ones in GeoGebra. So now the next question is, now we want to talk about measuring these things. And we'll talk about that a little bit in the next video.